This has been a bit of a journey for us. We actually started working with Augment a couple of years ago, and we got more and more focused on blasting and its impact on particularly the reconciliation process, and particularly when the mining engineers and the mine planners and the plant people, and they want to have debates about your block models and you want to defend where you're going. And it kind of forces you to think a lot more about what's going on through that process. A couple of points. We are using Augment software. Now you'll see terms like BMP and QBIs, and these are all earlier names of software. It all means the same thing, so it's all OMP, so don't get put off by that side of things. The other thing you'll see, I use the term data mine. I'm referring to Studio IRM. I cannot change the habit of a lifetime. It's data mine to me. Okay. By means of a background and put into context, for those who don't know, First Quantum has interest in nickel mines and copper mines, but they're basically a copper miner. In particular, large open cut copper mines. We produce about 800,000 tonnes of copper per annum. And you're looking at mining 10, 12, 15 metre benches. So, for example, at Cobre Panama, they process 90 billion tonnes of ore per annum. So these are big operations. The three big places where all copper comes from, 3 main mines, there's 2 in Zambia and 1 in Panama itself, one I've just referred to. So that's the backdrop. So we're going to talk a little bit about movement prediction from blasting. I will not be rehashing Bryce's talk, or trying not to rehash it. I certainly might be answering complex questions about machine learning. Our involvement, or particularly my involvement, was really integrating what Bryce's work was into Datamine and building the system around that. The original ideas for all of this actually didn't come from me. They came from David Gray, who's at the back there. You should raise your hand. It's all his fault. And he wrote all the original macros for the process. And then as time went on, we developed the system and actually made it a lot more robust and easier for people to use. Ultimately, robust is the magic word. And what have we learnt? I don't fancy planning on making any forward statements, but if I do, there's the usual cautionary note. Okay, so here we are, very standard sort of blasting thing, start from in-situ copper all the way up through to the mill at the very end. The arbiter of the truth, whether you like it or not. And each one of those processes involves moving material around. Blasting, you're looking at dilution, changes, things that you can't always avoid, but you can try and minimize it. But a lot of this journey that we've been on is really trying to understand what's going on at each step for those robust discussions during reconciliation talks. So what are we talking about? Talking about change the position of rock, and this is it. You are moving, literally are moving things around without overstressing the obvious. You're obviously going to be mixing things. So you're going to get dilution, contamination, and you're going to lose metal to waste zones or loss. Now, the degree of impact depends on commodity, geology, scale of mining, and of course, blasting practices. It's not going to be material to all mines that do blasting. So for example, we own the Ravensthorpe mine. It has its fair share of challenges, but blasting isn't one of them. Very, very low powder factors, about 0.3. So we don't have to worry about movement down there. But we certainly do in these big mines in Zambia and Panama. So we talked a little bit about conventional methods, markers, or purposeful markers with transmitters, and we've gone down this path as well. There are issues with these things. You do require to drill dedicated holes. The markers need to be surveyed. Sometimes they get destroyed. We had issues with particularly the transmitting markers where there's lots of pyrrhotite around and we couldn't pick the signals up, particularly with deep, thick benches. And the other issue they tend not to be actually representative of the body itself. So the density, for example, of a pipe or one of those transmitting markers is not going to be the same as rock or blasting. So when you start moving things around, it's going to behave differently. These tools all do work to a reasonable extent. but they do have limitations, and you can't use them on a blast by blast basis. So it's the gentleman at the front. He's been using another software solution, and this is where things are going. It's increasingly going to be software solutions. There's a couple out there now, and that's definitely going to be the trend. There'll always be a place for physical markers, spelling their demise, but this will be where people are going to be increasingly focusing their attention. So what's the key challenge? There is no reliable method for implicitly measuring movement. And therefore, whatever you do is an estimate. It's not a calculation, it's an estimate. Yeah, you can't get around that. But you can classify blasts to multiple types. Those of you who come from an open pit environment, generally blasting will be 2 or 3 different types, sometimes 4 or 5. Data sets can be collected from multiple types to actually quantify their behaviours, and as we've talked about several times, or Bryce has, we know where all the pre and post blast volumes are based on these high resolution surveys. So you know that all the blocks in the pre-blast volume have got to be moved to the post-blast volume. And that's the trick. So, got a case study here from Kansanshi, which is one of the 2 mines in Zambia. And for our example, we're going to pick on a just standard sort of blast from there. This is about 240,000 tonnes, 80 by 70 meters, as marked out by the arrows. Now, the blasting direction is from the north to the south. We'll show you the data that controls it. And here you've got 2 open faces. So the eastern face is completely open. It's a bit hard to see based on the picture. And the northern face is partially open. So this is a 10-meter deep blast, but that ditch there, if you like, is only about 5 meters. So it's partially open. So with the blasting initiating from north, moving to the south, the bulk of the material is going to be moving north, not surprisingly. But because you've got that open face to the eastern side there will be spill from there as well. So this is what it looks like after the blast. So you're looking about moving about 25 meters. You'll see that half filling has been completely filled, and the open area has spilled out through there. You've got quite a pronounced power trough on the southern end of the blast. And if you look at the material away from the open edges, it's fairly smooth. So the standard material has moved largely up and down. It's obviously moved laterally as well, but it hasn't broke through. So there's been a reasonable containment of energy in terms of the stem material there. It's broken through a little bit. You can see that lumpy bit down towards the bottom right here, but it's okay. It's blast go. So if this will play, there we go. So the first line of holes towards the back there was some pre-split holes. These are holes which are fairly lowly charged. The idea is they're to crack rock, they're not to move it. The charge is then kicked across the front as promised, and the rest they say is history. So what have we got to try and model that? So when we're running OMP, the base attempt is to put together a block model. We have gone through a process in the past where we'll combine individual models on a blast by blast basis, but it gets quite time consuming. And in the end, we found it was easier just to work with the large deposit scale models, and we pull out subsets of blocks from that model. As Bryce was mentioning, the resolution is 1 by 1 by 1 meter blocks. And so that resource model there has been chopped up into 1 meter cubes. And that's the raw product that gets fed into the Augment software. This blast goes about 1% copper. The veining you see is actually chalcopyrite veins, so it's a standard sort of Zambian copper belt type deposit. Kansanshi is unusual because they also get these large sort of chalcopyrite veins ranging from a few centimeters thick to meters thick sometimes. And they can run across the full breadth of the deposit. So like all these mines and these large bulk processing mining, yeah, dilution's a big issue. You can see those high grade veins there and the surrounding low grade material. And this is really the key to it, the blast data and these surveys. So here you've got the pre-blast with the half-filled trough and the open edge there. Then you've got the post-blast over there with your power trough at the back. You can see it's kicked through and filled that ditch, if you like, and then it's sprawled out over the edge there. So we've got a block model. Importantly, we've got the pre and post-blast surveys. You know where it starts, we know where it's got to end. And this is a similar thing, but this is actually comparing the differences in thickness. So to the left there, you've got the main thickness, which is where it's flooding into the post-blast, that trough there, that partially open bench. It's spilled over to one side, the far edge, and then you've got that thickness down the back there with the power trough. But this is really the key to it all. It's the blast setting, we call it the blast settings file. It is in essence the blast design file. So the engineers compile these for every single blast, and it's a CSV file. And the key components has timing, obviously the XYZ locations, I should say. It's got timing, the stemming depths, the hole depths, the amount of explosives loaded down the holes. They say timing is everything. Well, it's definitely very critical in blasting because this determines A, where things move and the nature of how they move. So the burden relief, which you can think of as like the time between the holes, the shorter that timing, the more things tend to get thrown around. Whereas if you make it two things, you just don't get enough fracturing. So it controls the whole behavior, or a significant portion of the behavior of the blast that you see. And this is where a lot of blasting goes wrong. It's not the design's poor, or what they're trying to do is poor. A lot of it just simply executing, not drilling holes to the same depths, not putting stemming in properly, having holes that they don't backfill. And that's where things start to go awry. And this is when you start seeing ugly blast videos. So we use Augment software to move the model. And we talked a little bit about training. So let's pick on Kansanshi. Kansanshi has 5 main different blast types, and we collect blast data sets from each of those blasts over an ongoing period. We try to get 50 or more, but it takes a long time. And we'll try to get those for all the different blast types. And one of the first things the Augment software does is classify what type of blast is this. Is this a center lift blast? Is it an open face blast? Is it partially open face blast, like the one we've been looking at here? And then it applies its algorithm depending on what type it's dealing with. The system runs as a series of CSV files from Datamine. And Datamine actually runs the OMP software via a script. So people running the system don't know anything about OMP. It's just this black box that turns up and it runs for about 5 minutes and then it closes up again. That's all they really know about what's going on. The deliverable from Augment is CSV file, effectively with new locations. So a new set of XYZ coordinates. So it's the same input model with all the original fields, but now has a new set of XYZ coordinates for each of those blocks. So X thousand blocks go in, X thousand blocks come out. So one of the basic checks that we have is there's no metal lost, or there's no blocks lost, or indeed gained. So yeah, all blocks get moved. Metal in equals metal out. As Bryce mentions, we add air volumes, because obviously the swell volume will be larger than the input. Once that model is then reloaded back into Datamine, we reblock it to the SMU size for markup purposes. And as part of that process, it merges the in-situ blocks and the air blocks, and it deals with the just density adjustment. Obviously, density will be less. So there's an example there. There's my copper model again. And then you've got the move bottle that comes out of rise. So that's what goes into Augment. Augment gives us a CSV file back. We reload that back. It's Datamine and add in back in all the air blocks. So the air blocks are just 1 by 1 by 1 blocks with things like density and all the grade fields set to 0.0001. Very, very low value. So the question always comes up with this, and I've said that it's an estimate. How do you validate this? So Augment have their own checks and balances. For us, what we're trying to work out is, does it make sense? Do we think it's really real, or as real as it could be? So the checks focuses on mechanical things like, have we lost or gained metal, but also, does it make sense? Are the patterns of movement what we'd expect? We have a guy in our Perth office, and all he does is blasting. He spends his time doing blasting, spends time doing with blasting engineers, trying to improve their patterns, trying to improve the way they do things. That's all he does. We spend a lot of time chatting to him about it. So we're then liaising with him about what he's expecting those moves to be, and then we're relating those back to what we're seeing in our model. After the quality of the blast, this is an ongoing challenge. Are the displacements reasonable? Then it shouldn't be excessive. So in this case here, the way that we tabulate this is again all driven by the system. We export a series CSV files into a dedicated folder. And then in terms of that, we look at that in a Power BI spreadsheet, which is a bit noisy, but that's actually the simplified version. But once you get your eyes into it, it's actually not quite as horrible as it looks. So at the top left, you've got metal in equals metal out. That makes sense. We've then got the degree of blasting, dilution, and loss. And so we're looking at, based on the inputs and then the reblocked inputs, how is the metal changing? How is the tonnage changing? So we're trying to get input on what that will be. So some blasts are going to be more risky than others. The grades are quite similar, and there's no distinct high-grade, low-grade zones. You won't see too much dilution loss. But if you've got pronounced, obviously, low-grade zones, then adjacent quite high-grade zones, then yeah, the risk suddenly gets a lot higher. The box down the bottom there on the right-hand corner is titled Principles of Homogeneity. That's all to do with distribution of air blocks. Now, we'll talk about being practical with this process. We've gone through a long path with BMP. At one stage, the process was taking up to 20 minutes to run, and we're trying to come up with all sorts of wonderful ways to speed things up. As things have developed, it's much more efficient. It's got smarter. Essentially, it's been a learning curve, both for us and for Augment. And now it's running a lot faster. So we don't get too caught up about the air blocks, except to keep it as evenly distributed as possible. Now, some of you look at the audience, well, that's not really fair. Surely there should be more air blocks towards the top than down the bottom. And you say, yeah, that's probably fair enough. But the issue that we were hitting at one stage was trying to deal with that was just creating more heartache than was worth. So you learn to be very pragmatic with this process, and look, just distribute it evenly. For our purposes, that will do. Moving to this side, you've got compliance with bearings. So you've got the plan vectors and then the actual vectors, because when we load the model, we've got the original input coordinates, and then we've also got the output coordinates, the move ones. So we actually look at the vectors. We can see how each individual block is actually being moved. We can compile stats on that. We can compile directions. So this is just running rows diagrams. So in that case there, that's pretty good. In the middle there to the top there, you've got the displacement vectors, and this is where we're looking at the amount of movement in the different zones, specifically stemmed, charged, subdrill. We're obviously going to want to see the most movement in the charge zone, lesser amounts in the stem zone, and minimal or no movement in the subdrill zone. At the moment, the algorithm that we're running, we've got it at 0. Again, we were having some issues where it was just moving the subdrill too much, and for the amount of impact that it was having on our blasts, it just wasn't worth fiddling around with. So I said, look, just don't move the subdrill for the time being. We'll come back to that. And then last but not least, up the very top there, right there, we give it a score. So we look at a whole series of vectors, or factors, if you like, in terms of swell, movements, and we compare that to a series of vectors. Some are good, some are bad, and we come up with a score out of 10. So in this case, last M11, 1265, B12 has come up with a score of 7.5. So like a lot of these measures, it gives you a relative measure. So around 7 point, that's pretty good. If you're getting 5s, things aren't things aren't going well. And you'll start to see misbehaving, well, poor results in some of these other statistics. So it's a measure on the day, but it's also very much a comparative measure. When you get new training done, do the scores get better? So how do we set all this up? Originally, we were doing grade control systems. We've had off-the-shelf systems by way of the background. We had issues though in that it didn't have the flexibility that we need, and we'd quite often have to change things, particularly like Colorado Panama was a new mine at the time. The rules kept changing. They wanted to do different things. So, okay, we've got to change this. Fine, we'll make it work. So we needed flexibility. So we started doing grade control systems about that time. And the other thing we quickly did is internet can often be problematic. So we very quickly went to a client server type thing. All processing is done locally. Trying to do things on servers is not going to be. So everything's done locally, and then the products or the deliverables of the process get copied to a server. The whole thing is driven by Datamine script-based menus, and we'll go through some slides just showing those. And it does all the processing, it does all the graphical component of the process. So this has all been set up using JavaScript, HTML, Microsoft's file system object. All the processing is done using a combination of Datamine macros and scripts. And an overlying thing about the way these things are designed is there is no typing. So people using the system can't type anything. They can select from pull-down menus, they can select files, they cannot type anything. So they can type things and they can break things. The system becomes much more robust by using that approach. So the next series of slides just show you how it sort of works in Datamine world, GORM world. So we've got an expandable, contractible menu up the top there, which controls the main steps. In this case, Kansanshi has a number of deposits, but really we're just going to focus up from markup selection, blast data, move model, always markup and plotting, export. So they can expand and contract that to keep the customization window as big as they want it to be. So the markup selection is realistically the first part of the journey, if you like. They'll select a model, so this is going to be a deposit scale model. They'll select their blast perimeter. Now these lists are populated automatically based on the local, there's a folder structure in the set which has blast settings files, design files, wireframe files, and he just makes lists of everything there and populates those pull down lists. They can do in-situ type blasts for free dig stuff, but most of the time it's blasted. And then they select the flitch section. So for Kansanshi, it's 10-meter blasts. It's either a single flitch, flitch D, in that case, or 2 5-meter flitches. The rest of the information, and you notice a coloured, a grey type thing, is purely for information purposes. They can't change it. They can click on there and they'll just get a message saying you can't change it. So it's all pull down menus. The top there, you've got options there. If they want to pull down data from the server, they can click on that and it'll then pull information down the server automatically. So you control when you want to refresh things. So what is the deliverable? Well, obviously you've got the surfaces down there, the blast settings file, that drill hole file. Effectively, think of it as a survey drill hole file with actual blast holes, the perimeter file, and a subset block model. The next bit, fairly straightforward. They can change legends and stuff if they want, but since you've got 2 buttons, load blast data or save blast data, that's it. So the load blast data, it'll load the pre and post blast surfaces, it'll load the drilling, it'll load that thickness model that I referred to before. And the goal of the exercise is to edit the pre and post blast strings. So in that case, the red string is the pre-blast string and the orange is the post-blast string. So the strings generally run along the edges of the drill holes and the toe of any open faces. So what you're saying is that this is the volume that will be moved. Anything outside that, those perimeters, that input perimeter will not be moved. Here I've got just a subset 3D window where I'm showing the post-blast spring. So quite often the best thing to use when putting the post-blast string, you can use the wireframe if you wish. Generally, people just use the sheets tab, so click between the different data types. You pick whatever works for you. In this case, they've run that orange string, the post-blast string, along the outer edge of the thickness model. So the third bit, move the model. So once all that data's there, you're pretty much ready to go. So move and reblock. It's got lots to do. So it runs a series of macros, and what it does is takes the block model, chops it up into the cubes. It estimates all those factors, timing, explosives, stemming heights, all that sort of stuff. Estimates all that into the block model. And then it runs OMP, and then waits for it to finish. Once OMP is finished, for Kansanshi, it takes about 5 minutes these days. Once it's finished, it loads it back in, and effectively that one-by-one block model that you saw before. And then it's got 2 sets of things to do. It compiles the reblocked models, one for actual markup purposes, the last one there. It also compiles other versions of the reblock models purely for validation purposes. The other thing it does is generate all those CSV files for the Power BI dashboard that you saw earlier. So literally hit move, go and get a copy, come back 5 minutes, and it's all done. They can, if they wish, view that one-by-one model if they like to, and they all seem to do that. But that's essentially that. The last bit's the markup, or the second last bit is the markup component. Again, most of the menus are grayed out, which means they can't change it. And they literally select the flitch, press load, set view, and it loads all the data into the 3D window. And they can digitize boundaries to mark out, to limit the different material types. And they use those outlines and evaluate outlines to generate tons and grade for each one of those boundaries. If they don't like it, they can press the clear results button and redo it to their heart's content. They want to really look at it in table form, they can just click that button and it'll load it up into Excel. So they do that process for every single flitch. And at the end of each time, they simply push that bottom blue bar, slave flitch dig plan, and it writes out the results. Coming to the very end, simple metals, really got 2 buttons, plot and export. Plot will generate, they can select the different outlines. So this has got 2 flitches, so you can select D or D flitch, and it'll generate a plot file for them, and make a PDF for them, copies it to the server. And then on the bottom, you can't see it in this case here, you've got a button where you push export, and it copies all the variant data files onto their server, for things like Wenco and so on. So it's all automated. Okay. So what have we learned? We continue to learn. They can deliver great outcomes, but we've also found they can deliver endless roads to nowhere. It's like the old song. And we've learned to be very hard-nosed about being practical. If it's just not working, then change track. As with any estimate, you need a certain amount of data before you can become comfortable that the result you're getting is reasonable. As Bryce mentioned, it's a rapidly changing field. This is going to be a moving feast for quite some time, not just in terms of software developers, but also in terms of machine learning. And back to that validation point, there is no fixed validation. There's no thing you can hang your truth on. You have to rely on observations and your understanding of how things should behave. Training takes time. So we compile the blasts. It's a well-known process now. So we compile the blasts and we send them off to Augment, and they do all the training, and then they'll give us a new version of software that runs with it. So be ever the pragmatist, don't muck around if it's not working. And understand the context of your opportunity. You're going to need their help. You're going to have to make the blasting engineers your friend. You're going to have to make the production engineers your friend. And you may not necessarily spend too much time talking to them. Blasting. In a former life, I did consulting for about 10 years and saw lots of blasting, and yeah, it's quite variable. Not entirely sure why it is that variable. It tends to be done really, really well, sometimes average, or really, really poorly. It is quite variable. But some of the reasons are, often the site blast engineer is one of the most least experienced engineers on site. There should be somebody who's training them, and usually there is, but it usually just gets allocated to the last person who got onto site, and that obviously creates problems. So you might have problems with your blasting, but it doesn't necessarily mean they don't care anything. It might purely be inexperienced. Blast videos tell you where you are, where you really are. So even the blasting guy in the office, one of the first things we're talking about blasters is, can you tell me the video? And that's really where your starting point is. If you're not clicking those videos, you really are blind. There can be challenges and so on. Sometimes they haven't got time to do it. Sometimes the drones get attacked by birds of prey. Things do go wrong, but there's no real excuse for not doing it on a regular basis. Extensive lateral is the kicker. Doesn't matter how good your software is, your blasting practices are so poor, there's nothing you can do. We're looking at some blasts there, and the actual post-blast volume was smaller than the pre-blast volume. And the reason was they put half it into the DRC. So it's very much an education tool. It's not about beating people up. It's about improving things from everybody's point of view. That's winning hearts and minds. You want to make friends. You want things to get better. So the open bit geos in there. Try and get a hand of understanding of basic blasting practices and what the implications are. If it looks ugly, maybe it is. There are exceptions, so don't assume that it's poor. It's always good to see what they're doing. And as I said, it's not going to be an issue for all mines, low powder factors, soft rocks, or what have you. No selectivity. So, what are the conclusions from Datamine? Well, those of us old enough, Datamine are actually still relevant after all these years. It's still relatively simple to learn, and mining is a repetitive task, so it's perfectly set up for it. Scripting's allowed us to construct robust interfaces, and they can be used to run macros and communicate with them via stack files. And there's lots of great stuff on the internet. So, for example, all that interface was based on open source stuff that I got searching the internet. But learning curve for scripting is much steeper than macros. It's definitely not going to be for everyone. If you're keen, I suggest you get help from Datamine or a consultant, friendly consultant near you. And there are, of course, off-the-shelf alternatives if you choose to go down that path. So lots of ideas, something here to think about. So what's it all been worth? So we've been working on this for several years. It's too early to gauge the impacts of Kansanshi. It's still very new, but certainly the Sentinel mine, where we compare markup grades to predicted markup grades, we've seen improvements around 2–5%. And so for these blasts, that can easily translate between $100,000, $200,000, $300,000. So it's been a lot of work, but in that context, it's obviously worthwhile. Questions? Yes.
This may be null and void in the sense of the scale of your operation and your body's position here.
Yeah.
But the grade control model which you produce, I can start there, it's just running a copper percentage. Do you only run copper percentage? As part of that grade control model, have lithological and mineralogical controls based on those chalcopyrite veins. I just find it difficult to wrap my head around the fragmentation of the chalcopyrite veins being homogeneous to that.
So you're talking about difference in fragmentation as to chalcopyrite sulfides with quartz as opposed to disseminated sulfide. At this stage, we don't distinguish between the two. We're just blasting the mats. So we don't try and model that. Is it worth worrying about? I'm not sure. I suspect not. Just simply, as you say, it's a scale thing. But it's like all things, you keep an eye on it.
The other one would be when the summary page, you're creating a swell factor. It's not a universal swell factor, which is commonly used.
Yep.
If you are a client contractor miner, is that something which you could then put onto the contractor? And they are coming to the end of the month, and you are adjusting your PCMs based on they're going to then question this, question the validity.
Well, the issue then you've also, because Swell is obviously not just so I'm assuming, okay. So the question is, if the blasting, are you speccing out performance in terms of the contractor, in terms of how they do the blasting? Is that correct?
Yes.
Haven't thought about that way. All the blasting is done in-house. That's not a bad idea, actually. Yes.
You're getting a, say, 2 to 5% improvement on the reconciliation of the mill. If this improves selectivity of ore and weight, did you do any validation of material receptive waste or low-grade stuff to say that did actually cover that grade bin, or have you sent good material?
Okay, so the question for the tape is, do you look at drilling supposed waste dumps and so on like that to see just how good or bad you are? The answer is no. It's a good idea. I think quite a few people recommend drilling waste dumps sporadically, but we don't do it.
This process allows you to mark up to say, yes, that is now the low cut-off grade, and now it's now a full cut-off grade, depending on where it's flat. But just an extra check to say, yep, the AI did its job, and I haven't done it.
Oh, very much so. But it's even if you're not doing blast movement at all, it's not a bad idea. But at the moment, no, we don't do that. Anyone else? Done.